Welcome back. Well, let's look at some more examples of using a trigonometric substitutions to find antiderivatives. Okay, there we go. Let's start out with something like this. Alright, so remember our two basic substitutions are a sine substitution and a tangent substitution. If we see 1 minus x squared, we're looking at a sine substitution. If we see 1 plus x squared or x squared plus 1, we're looking at a tan substitution. Since what we're looking to substitute in here is the 64 minus x squared and we see the minus sign, that really means that we're looking at a sine substitution. This should be a sine substitution, but the 64 causes a little bit of trouble. What we really want is we want that entire x squared to be 64 sine squared theta. So that then we would be able to factor 64 out of the x squared. And we'll even write that out. So 64 minus x squared, the stuff under the radical, is 64 minus 64 sine squared theta, which is 64 times 1 minus sine squared theta, which is 64 times cosine squared theta. Which means that if we apply the radical, we get radical 64 cosine squared theta, which is 8 cosine theta. Everything needs to be transferred over to theta. So x squared, that's great, we already got it. X squared is 64 sine squared. This radical is 8 cosine theta. Don't forget your dx. That's the most common mistake, forgetting the dx. To figure out what dx is, we need to take our initial substitution, solve for x, which makes 8 sine theta, by taking the square root, and then finding dx. So dx is the derivative of this, which will be 8 cosine theta. Now we can substitute everything in. X squared is 64 sine squared. The radical is 8 cosine theta. And dx is 8 cosine theta. Sorry, I forgot my d theta. Derivative is 8 cosine theta d theta. So 8 cosine theta d theta. And let's not forget, so we're going to need a couple things. The most important thing that we need for the final step after we take the integral is this one, because that tells us what our substitution was to convert it back into x's, from thetas to x's. So let me just save that one. X was 8 sine theta, and everything else we can get rid of. So we essentially use the substitution. X is 8 sine theta. At this point, we can cancel our cosine theta and cancel our 8, and the integral becomes d theta over 64 sine squared theta. Which is the integral of 64, or it'll be cosecant squared theta, with a 1/64th out front. And this is one of our basic trig antiderivatives. Remember that the antiderivative of secant squared is tangent. This is very similar, so we can remember it. It's exactly analogous. The antiderivative of cosecant squared is cotangent. So we get 1 over 64 cotangent theta d theta. Alright, now we do need to make a backward substitution now to turn it back into x. If x is equal to 8 sine theta, that tells me that that x over 8 is sine theta, so that sine theta is x over 8, so that theta is sine inverse x over 8. So this is 1/64th cotangent of sine inverse x over 8 plus c. Now, a few things. This is good enough for me. I am fine with this on a quiz or a test. My math labs is going to require one extra step. And so let me talk about how we're going to make this one last step to make it look prettier, to look nicer. This is kind of a mess, cotangent of sine inverse. So we can apply some trigonometry ideas to make that look a lot nicer. So let's talk about that. Cotangent of sine inverse of x over 8. That's what we're looking for. Okay, so here's what we're going to do. We're going to make a right triangle. And we're going to set up a right triangle that has essentially what we want, right? So sine inverse of x over 8. Sine is opposite over hypotenuse, which means that I'm going to put x here and I'm going to put 8 here. So that if this is theta, theta is sine inverse of x over 8. Because sine of theta will be opposite over hypotenuse. So I draw a right triangle using what I have here. We'll see some more in the future with cosine inverse or tangent inverse, but we just set it up so that the angle makes what we have on the inside. X over 8 with sine is opposite over hypotenuse, so this is opposite, this is hypotenuse. So now what are we looking for? We're looking for cotangent of that angle. So that theta, in this case sine of theta, is x over 8 from my picture right here, so that theta is sine inverse x over 8. Which means that what we want is cotangent of sine inverse of x over 8, which is cotangent of theta. That's what we want. We want cotangent of theta. Cotangent, tangent is opposite over adjacent, so cotangent is adjacent over opposite. But since this is a right triangle, we can use the Pythagorean theorem to say that this has got to be the square root of 64 minus x squared. Right, so this squared plus x squared is 8 squared, so this is the remaining piece on our Pythagorean theorem. So cotangent, instead of opposite over adjacent, will be adjacent over opposite, which is root 64 minus x squared all over x. And what we've just discovered then is cotangent of sine inverse of x over 8 is this much nicer looking 64 minus x squared square rooted all over x. So we'll do that with some more as we continue on, but this is how we need to go from our integration, our final step of an integration, which is correct but messy. We'll often have a trig and then an inverse trig that don't match up. This is how we take these two trigs put together and convert it to something that looks a lot nicer. Okay, so let's look at another one. Alright, how about integral of square root of 16 minus t squared dt? Again, this will be a sign substitution because it's minus 16 minus t squared. We want t squared to be that the t squared has to have a 16 with it so that we can factor the 16 out. But since it's a sign substitution, it'll be 16 sine squared. So that 16 minus t squared is 16 minus 16 sine squared, which I can factor 16 out and get 1 minus sine squared. Which is 16 cosine squared theta. So the radical 16 minus t squared will be radical 16 cosine squared, which is 4 cosine theta. dt, remember that we need to solve for t. T is equal to 4 cosine theta, d theta, t is equal to 4 cosine theta, dt will be the derivative of that, which is 4 sine theta, but negative. So negative 4 sine theta d theta. And now we can transfer everything over to our thetas. The radical is right here, 4 cosine theta. Then dt is negative 4 sine theta, d theta. We're going to need to save this one for our last substitution, back substitution. So the t was 4 cosine theta. That's essentially our substitution that we've made. And we find our integration. This integral becomes negative 16 outside the integral, then cosine theta, sine theta, d theta. And this is a trig integral from the previous section. Remember, if we have a mix of sines and cosines, I can let u be, in this case I'm going to let u be sine theta, so that du is cosine theta d theta. So if u is equal to sine theta, du is equal to cosine theta d theta, and that's du right there. So this integral is negative 16, integral of sine theta, which is u, cosine theta d theta, which is du, so that's u du, which is negative 16u squared over 2, which is negative 8u, which is negative 8 sine theta, plus c. But we need to return it to t, our original variable. So this one is a weird kind of process where we had to first use a trig substitution, and then as part of the trig substitution we needed to use a u substitution. So we ended up with u, which then we convert back to theta, but we're not done because we need to convert it back to t. And that's why we saved this one. Divided by 4, I get t over 4 is cosine theta, so that theta is cos inverse t over 4. And that makes, so that makes negative 8 sine of cosine inverse of t over 4. Plus c. And then we're still not quite done, because we need to do something similar to what we just did a second ago in the previous example. That sine of cosine inverse looks messy, so we're going to apply some clever trigonometry to convert it back into something which looks a lot nicer. So we've got negative 8 sine cosine inverse t over 4. That's what we've got. Alright, now we're looking at cosine inverse of t over 4. We draw our right triangle, and theta will always be here, so we always start like this. But now cosine is adjacent over hypotenuse, which means I'm going to put t as the adjacent and 4 as the hypotenuse. So that now cosine theta in my picture is t over 4. And the theta that's in the picture is cosine inverse of t over 4. So this inside is now the theta in the picture that I made. Now I want sine of that theta. So we need to apply our Pythagorean theorem to get this one, which will be the square root of 4 minus t squared. And now sine of this is opposite over hypotenuse. So the sine of theta is root 4 minus t squared all over 4. And so this then simplifies to minus 8 sine of theta, but theta is cosine inverse of t over 4, so this whole deal is what we have. So minus 8 times root 4 minus t squared over 4 plus c, which is 8 and 4 make negative 2, root 4 minus t squared plus c. And that's the answer. Let's do another one. And so let's look at another example. Let's integrate square root of 196 minus t squared over t dt. Again, we see the minus. When we see the minus, that indicates that we'll be looking at a sign substitution. So we want this to be a sine squared, but we need the 196 as part of it as well. So we need t squared to be 196 sine squared theta. So that what's underneath the radical is 196 minus 196 sine squared theta, which factors out, the 196 factors out, and I get 1 minus sine squared, which is 196 times cosine squared theta. We're taking the square root of it, which is, this is 14 squared, so 14 cosine theta. We need to transfer everything over to t, so we'll need t and we'll need dt. If t squared is 196, then t is 14 sine theta by taking the square root. Remember, we'll need to save that. That's our main, that's essentially our substitution. This is the trig substitution that we're using, although we don't really get to it till later on. So we'll definitely need to keep that. And then we also need dt by taking the derivative. If I take the derivative, I get 14 cosine theta. So now we can make our substitution. The numerator is this radical right here, which is 14 cosine theta. The denominator is t, which is 14 cosine theta. 14 sine theta. And dt is 14 cosine theta d theta. There should be a d theta there as well. So 14 cosine theta d theta. We simplify as much as possible. The 14s will cancel. And we're going to see integral of this 14, I'll pull all the way outside of the integral. So this is cosine squared theta over sine theta d theta. And then we need to apply some algebra tricks here to finish this integral. What I'm going to do is I'm going to turn cosine squared into 1 minus sine squared theta. And then I'm going to divide the sine squared, or the sine theta, into both parts. And I get 1 over sine theta minus sine squared over sine theta. Which is 14 times cosecant theta, 1 over sine is cosecant, sine squared over sine is sine. The antiderivative of cosecant is not an easy integral. This is not something that you'll be required to memorize or be able to derive. There's a lot of tricks that go into getting it. For this problem, there you have a similar question to this on the homework. It's okay just to look up the antiderivative or to remember it from what we're looking at here. But in general, the antiderivative of cosecant theta is negative natural log absolute value cosecant theta plus cotangent theta. It's definitely not an easy integral to come up with, but we'll just use that. We'll use that fact, which means that this is 14 times negative natural log absolute value cosecant theta plus cotangent theta minus the integral of sine theta, which is negative cosine, so that makes plus cosine theta plus c. Now we're going to have to convert our thetas back into t. But we can do that from right here. If I divide by 14, I get sine theta, so that theta is sine inverse of t over 14. So we're going to put that back into our result that we have here, and that leaves us with 14 times negative natural log, absolute value, cosecant of theta, which is sine inverse t over 14, plus cotangent of sine inverse of t over 14, plus, that ends the absolute value, plus cosine of sine inverse of t over 14, plus c. And now we'll have lots of practice using our tricky trig triangles to convert these trig inverse functions into something that looks prettier. On the outside, all three of the inside pieces are the same. Sine inverse of t over 14, which means that we'll be using the same basic triangle. So remember, we start with a right triangle that looks like this. We put theta right here, and then we look at our inside piece, sine inverse of t over 14. Sine is opposite over hypotenuse, so the opposite is t, the hypotenuse is 14. Which means that by the Pythagorean theorem, the other side is the square root of 14 squared minus t squared. So that's square root of 196 minus t squared. That's our trig triangle that we're using to get the inside piece. Then we just apply the trig that we're looking at. Cosecant. Cosecant is 1 over sine. Sine is opposite over hypotenuse, so this is hypotenuse over opposite. Hypotenuse over opposite is 14 over t. So that's the cosecant. Cotangent. Well, tangent is opposite over adjacent, so cotangent is adjacent over opposite. Adjacent is root 196 minus t squared, and opposite is t. Finally, cosine of this angle, cosine is adjacent over hypotenuse. So root 196 minus t squared over 14. And that's our final answer. Let's do another one. All right, integral of dx over 1 plus x squared to the 3 halves. All right, now we've got one with a plus. So plus should indicate to you that we're looking at a tangent substitution, since 1 plus tan squared is secant squared. So and this is as simple as it can get because it's 1 plus x squared. So I want x squared to be tan squared, theta. So that 1 plus x squared is 1 plus tan squared, which by a trig identity, in this case, is secant squared. 1 plus tan squared is secant squared. Which means that we'll be able to sub in for the denominator. Sorry, I don't want 2x's there, I just wanted a single dx. But we still need to know what dx is. And we get dx by taking our first piece and solving for x, in this case by taking the square root. And I just get that x is tan theta. Remember that we're going to save that when we have the x equals, that we want to save that for our final backward substitution. If x is tan theta, then dx is secant squared theta. The derivative of tangent is secant squared theta, d theta. So we can make our substitutions in. Dx is secant squared d theta. 1 plus x squared is secant squared, so that's secant squared to the 3 halves. Then we simplify. This is secant to the 2, and this is, well, let's just look at the denominator first. Secant squared to the 3/2. When I have something, an exponent to an exponent, the exponents multiply. So that's 3/2 times 2, which is just 3. So that's secant squared theta over secant cubed theta. Which is just secant theta. And this is actually very analogous to the example that we just looked at in the previous situation. In the previous question, we ended up trying to integrate cosecant, and we found negative natural log absolute value cosecant plus cotangent. This is secant rather than cosecant. What we end up getting is almost the same thing. We get the secant theta plus tangent theta, so the cos are gone. The only real difference is that it's not a negative. That's just the way that things work out. And this is really our antiderivative. Now we do need to convert it back into x. We convert that one back into x using this. If x is tan theta, then theta is equal to tan inverse of x. If theta is tan inverse of x, then this becomes natural log secant of tan inverse of x plus tan of tan inverse of x plus c. And we'll need to use our trig triangles to convert these back. So let me rewrite that. ln absolute value of secant of tan inverse of x plus tan of tan inverse plus c. Now the tan of tan inverse, that's easy. Right? Sine of sine inverse, they cancel each other out. Tan of tan inverse, applying an inverse function with the original function undoes the function, so this will just be x. The tan of tan inverse of x is just x. This one we do need to use a triangle though for. Tan inverse of x, we'll start with the same. Tangent is opposite over adjacent. This is just x, so we need to think about that as x over 1 in terms of a triangle. So that opposite over adjacent is x over 1, which means that by the Pythagorean theorem, this is the square root of 1 plus x squared. Secant is 1 over cosine. So cosine is adjacent over hypotenuse, so we're looking at hypotenuse over adjacent. So this will be root 1 plus x squared over 1. So it's the opposite of cosine. Cosine is 1 over this. We want the reciprocal of that, and we get root 1 plus x squared over 1. So this is ln absolute value root 1 plus x squared plus x plus c. And that's the answer. Okay, let's look at another one. We'll look at integral of 1 over 64 plus x squared dx. Again, we see a plus, which indicates tangent substitution. Because of this 64, I need x squared to be 64 tan squared, so that in the next step we'll be able to factor out a 64. So then we can factor that 64 out. I get 1 plus tan squared, which is 64 secant squared. 1 plus tan squared is secant squared. So that's the entire denominator. We'll square that, but we also need dx. And we get that by first going to x is equal to 8 tan theta, which we'll save for later. And then taking its derivative. Derivative of tangent is secant squared, d theta. So we then make our substitutions in our integral. And I get 1 over 64 plus x squared is 64 secant squared, so I need that squared. So that's 64 secant squared theta squared multiplied by 8 secant squared theta d theta. Now we simplify this as much as possible. The secant squared up here will cancel with one of the secant squareds that are down there. So we end up getting a secant squared in the denominator. The 8, well 64 is 8 because it's 8 and then squared. So 8 will cancel with one of them. So that's actually 1 over 8 cubed. If you cube 8, you get 512. So this is 1 over 512. Secant squared, well secant is 1 over cosine. So secant, 1 over secant is cosine. So that's cosine squared theta d theta. And the formula that we want in this case is that cosine squared theta is 1 plus cosine 2 theta all over 2. Which then we're going to use some algebra to break into 1 over 2 plus cosine 2 theta over 2. So that the integral in question now is 1 over 512 integral of 1/2 plus cosine 2 theta over 2 d theta. So let's simplify that out and work on each piece separately. The 1/2 integrates to 1/2 theta. So the 512, the 1 over 512 is still there. We'll leave that out front for now. 1/2 integrates to 1/2 theta, since theta is our variable. The cosine of 2 theta. Well, the over 2, let's pull that out as well, so that all we're doing is integrating cosine of 2 theta. Cosine integrates to sine, but sine of 2 theta won't work because we get an extra 2 from the chain rule. So we need to actually get rid of that 2 as well, and we end up getting sine 2 theta over 2. Just think about it like this. If you take the derivative of sine of 2 theta, then we get 2 cosine of 2 theta. So that extra 2 would cancel with that, and that leaves me with exactly what I need it to be. And so this is my antiderivative. Finally, we need to convert this thetas back into x's. That's what this will be good for. So this is tan, if I divide by 8 and take tan inverse, I get theta is equal to tan inverse x over 8. So let's push the 512 through now. So this makes 1 over 1024. Theta is tan inverse of x over 8. Plus, this is going to be this times 2, which will be 2048, because I have 4 of them down here, sine of 2 theta. So that's 2 tan inverse x over 8. At this point, the answer is good enough for me on our written quiz or on our test, but on my math labs, again, we'll need to go back and to make this a little prettier looking. This one's actually a bit tricky, a little bit trickier than the other ones because of this 2 here. What we need to use is one of our other double angle formulas, and remember that sine of 2 theta is 2 sine theta cosine theta. There's nothing we can do with tan inverse. Tan inverse is tan inverse. We're not going to use a trig triangle to do anything with that because it's not like cosine of sine inverse or something like that. It's just tan inverse. There's nothing we can do with that. This, however, is sine of tan inverse. The 2 is the problem. So we're going to use this trick right here, this idea here, to take the 2 that's inside, pull it outside at the cost of using 2 trig functions. So 1 over well, let's just work on this one separately. So this is sine of 2 times tan inverse x over 8. This is like my theta right up in here. So this is 2 sine, and theta again is tan inverse of x over 8, times cosine tan inverse x over 8. So up to these constants, this first piece is there, we're stuck with it, we're not doing anything. This constant is here, we're also not doing anything with it. But we do need to simplify these. And each of these we can do separately because it's a trig inverse. Trig inverse. So we want sine of tan inverse of x over 8 and cosine of tan inverse of x over 8. And so we're going to use our triangle. So we're looking at tan inverse of x over 8. If this is theta, tangent is opposite over adjacent, so that's x and that's 8. That's tan of theta will be x over 8, which means that this last piece is square root of 64 plus x squared. That should not be surprising, that was part of the original problem. Sine of the angle now will be opposite over hypotenuse, so this is 2 times x over root 64 plus x squared. Cosine of the angle will be 8 over that. So that's times 8 over the same thing, 64 plus x squared. Putting this together makes 16x over 64 plus x squared. And that all goes in for this stuff that's right here. And we'll just put that together. So to finish the problem, I get 1 over 10, 24, tan inverse x over 8, plus 1 over 20, 48, times 16x over 64 plus x squared. And there'll be one last piece. You'll have to take the 16, that's 2 to the 4th, and this is 2 to something. And you'll have to simplify the 16 over 20, 48 before you enter your answer, but that's what it takes, and that's the idea. And let's look at another one. Alright, let's look at another one. Let's look at x to the 4th over 9 plus x squared. And again, we see the x squared, which should indicate that we're looking at a tangent substitution. So we want x squared to be 9 tan squared, so that the denominator is 9 plus 9 tan squared, and we can factor out the 9. And 1 plus tan squared is secant squared. The numerator is x to the 4th, which will be the square of this. So x to the 4th is actually 9 tan squared squared, which is 81 tan 4. We also need dx, which means we need x, which will be 3 tan theta. So the dx is 3 secant squared theta. We'll save our x equal 3 tan theta for our final substitution. Substitute everything in for the integral. X to the 4th is 81 tan 4. The denominator is 9 secant squared, and dx is 3 secant squared. D theta. Should be d theta there. Simplify. If we simplify, the secant squareds go away. The 81 and the 9 make 9, so that makes 27. Integral of tan 4. what to do. The derivative of tangent is secant squared. So if I can get, what I'm going to do is turn 2 of the tangent into a secant squared, so that I have secant squared in there, and then the rest will be usable with a u substitution. So this will be 27 integral of tan squared theta times 1 minus secant squared theta. Remember that tan squared plus 1 is secant squared. So that tan squared, sorry, I got that backwards. Good thing we wrote that out. So the tan squared is secant squared minus 1 if I move the 1 over to the other side. So tan squared is secant squared theta minus 1. Right, so that's tan squared, that's tan squared. And so that's 27 integral of tan squared theta secant squared theta minus the integral of tan squared theta when I distribute that in. Okay, now we're making progress. If u is equal to tan, then du is secant squared. So if u is tan, then this becomes integral of u squared du. Right? U is tangent, so that's u squared, and du is secant squared, so there's du right there, and so that is u cubed over 3 plus c for that first integral. So we end up getting, for this left-hand integral, u cubed, but u is tangent, so that's tan cubed theta over 3. Let's not forget about our 27. And then we need to figure out about tangent squared. So that's actually all that's left that's important from the board right now, how to integrate tangent squared. And that will go over here. We're going to write that as sine squared over cosine squared. We're going to take the numerator and write it as sine squared is 1 minus cosine squared. And then we're going to break it up into 2 integrals. 1 over cosine squared and cosine squared over cosine squared. So we can 1 over cosine squared is secant squared. And cosine squared over cosine squared is 1. Integral of secant squared is tangent, because the derivative of tangent is secant squared. And integral of 1 is theta. And that's everything that we needed to do for there. So what we've discovered is that this is plus tangent theta minus theta plus c. So this is a good trick for remembering tan squared. To convert it to sines and cosines and use some of those trig identities to make the antiderivatives work. Finally, we need to use this and trig triangles. So this is 27. Well, let's put the 27 in. So that makes 9 tan cubed theta plus 27 tan theta minus theta plus c. But if x is 3 tan theta, then that means that theta is actually tan inverse of x over 3. So that's 9 tangent cubed of tan inverse x over 3 plus 27 tangent of tan inverse x over 3 minus theta plus c. Well, tan cubed means the tangent of theta cubed. So this is really tangent of tan inverse of x over 3 raised to the third power. But tangent of tan inverse, they cancel each other out, they undo each other, and so this is really x over 3 cubed. This is tangent of tan inverse, which again is x over 3, and we're left with this last one, which is tan inverse x over 3. We can just do some final simplifying to clean it up. This is 9, this is 3 cubed, so that actually leaves me with x cubed over 3. This leaves me with 9x minus tan inverse x over 3 plus c. And that's the answer. Let's do another one. Integral of x squared over 25 plus x squared squared. Again, we see the 25 plus x squared. So hopefully we're getting familiar with the process. We're going to let x squared be 25 tan squared. So the 25 plus x squared is 25 plus 25 tan squared, which is 25 times 1 plus tan squared, which is 25 secant squared. We've already got x squared, that's right there. If we square this, we get the denominator. X is 5 tangent, so that dx is 5 secant squared theta, d theta. We've got everything we need to make our substitutions. X squared is 25 tan squared. The denominator is this whole mess, which is 25 secant squared, and then dx is 5 secant squared theta, d theta. We'll save our original substitution. X is 5 tan theta, and simplify the integral. If we look at our integral, the secant squared will cancel with 2 of the secant squareds. This 25 will cancel with 1 of those 25s. So that leaves me with a 5 and a 25, which is a 1 over 5. The secant squared cancels with 1 set of secant squareds, leaving me with a secant squared in the denominator and a tangent squared in the numerator. We're going to apply a similar trick to what we just saw in the previous example. We can rewrite tangent squared. Remember that 1 plus tan squared is secant squared. So I can rewrite that as 1, tan squared is secant squared theta minus 1. All over secant squared theta. Break this up into 2 different integrals. The first one is secant squared over secant squared, which is 1. The second is 1 over secant squared. So that's 1/5. Integral of 1 minus 1 over secant squared is cosine squared. And at this point I'll let you finish it, because this is a simple integral. And this is one that we looked at in just one of the examples a few minutes ago, using a double angle formula to turn cosine squared into a cosine of 2 theta. So we'll stop right there. I've given you the basic ideas from that one. You should be able to finish that using the stuff that we looked at previously. All right, one more. 1 over the square root of x squared plus 64 dx. Again, we see a plus, which tells us tangent. So this is not quite in the same order. We were used to seeing things like 64 plus x squared, but with plus it doesn't matter, right? Plus, either order is the same. So I can still let x squared be 64 tan squared theta, so that x squared plus 64 is 64 tan squared plus 64. 64 factors out, I get tan squared theta plus 1, but tan squared theta plus 1 is secant squared theta. So the denominator is the square root of 64 secant squared theta, which is 8 secant theta. We also need dx, which we'll get by first solving for x. X is 8 tan theta by taking the square root. So that dx is 8 secant squared theta, d theta. We make our substitutions. The denominator is what we've just figured out right here, 8 secant theta. The numerator is still 1. Dx is 8 secant squared theta. The 8's cancel. I should have saved what our substitution was. Really the substitution was x was equal to 8 tan theta. So that x squared is 64 tan squared theta. But the 8's cancel and the secant squared cancels with the secant, and I end up getting just a secant theta, d theta. This is an integral that we saw before. I just mentioned what the antiderivative was. It's ln, absolute value of secant theta plus tangent theta, plus c. So this is ln, absolute value of secant of, from up here, this tells me that theta is tan inverse x over 8. So this is secant of tan inverse x over 8 plus tangent of tan inverse x over 8. I'll let you practice the last step. We do need to use some trig triangles to get to make it simpler as far as my math labs. Again, on a quiz or test, this is good enough for me, but for my math labs, you need to go that one last step using the trig triangles. I'll let you give that a go for this one. We've seen that lots and lots of times at this point. So we've gone over lots of different types of examples for these trig substitution integrals, and we'll see you next time.